Good afternoon. My name is Matthew Dickie. I am CTO of Group-BMC, a small startup focused on IoT and IoT security. I have a background of 30 plus years in security, IT security, cryptography and PKI. I have designed and managed many PKI solutions protecting financial services assets in environments with tens of thousands of nodes. Today, I propose to present the PKI as a ticking time bomb within an IoT environment. IoT, we hope, will take over the world, and following the general vision that has been proposed, a hyper-automation, hyper-connectivity world will bring new business capabilities for us all. The processing of the data collected in an AI sense in the cloud, if trusted and protected using technology such as blockchain, will bring new benefits to a variety of people across the globe. However, the reality of today is that only minimal standards exist, and most of it are purely at the technology layer and don't deal with the higher levels that PKI are frequently used. These are areas such as code signing, TLS, SSL. The go-to standard for that, therefore, is the current IT environment. Security, by definition, is applicable at all layers in the architecture and is becoming more increasingly complex at the data transfer levels and at the data level. This is predominantly due to drivers such as privacy and also confidentiality and the protection of intellectual property. Not all data goes to the cloud, although in the IoT world it's becoming an assumption that it will. In reality, this will not be the predominant use case for quite some time. No one knows the future. All we do know is our current thinking is inadequate to foresee the future or to secure it. PKI has been the go-to guy for the IT industry pretty much since the internet was developed. It is used holistically across all of the websites to end up protecting the data and to provide authentication and secure channel management. It delivers the basic key management capabilities for which to build higher value security services that protect the data. Connecting devices and from an IoT world come though with a much more nuanced risk posture and security strategy. Smart heart monitoring devices or insulin pumps have a totally different risk posture from built-in sensors built into automotive or smart appliances within a home. The one size does not fit all. So the model that you take from the IT environment of website protection using PKI may or may not support IoT. The availability of a management back channel in particular is required to change the code, patch the code, and ultimately to manage keys. The stakeholders that are required to judge the risk of a given business case must start to see the IoT environment as low risk or high risk. High risk environments typically will have a management back channel for patching. Low risk devices will typically not. The low risk devices will frequently be extremely constrained in their capabilities, battery operated, limited memory and limited CPU power, but they may still have to secure themselves or be secured within an environment to protect what they do. To determine what is required, you must first be really clear what the security service you're trying to attain is. The standard security services can be characterized by access control, authorization, data confidentiality. Difficult nuanced services like non-repudiation are not typically in scope of an IoT environment today, but the future, who knows? Availability becomes a common security requirement, but frequently the risk of having a PKI might actually clash with the ability to have a system which is available. Data integrity is either implicit or, I'll cover an example later, explicit when we deal with things like code signing. When looking at PKI, you must try to see the architecture of the PKI. To focus only on the P and the K, the asymmetric cryptography, the Alice and Bob model as is taught in most universities and most theory, is insufficient to understand PKI and to understand PKI within an IoT environment. The I part, the infrastructure, and in particular the operations, the policies, and the lifecycle management is fundamental to having a stable operating environment at an industrial scale. PKI is simple in theory, It's conceptually very simple. You have two systems that wish to talk to each other securely, and you have an intermediary, a trust broker, that establishes trust between the two, for which you can establish a key. The key can be based on certificates, asymmetric cryptography, or symmetric. When each entity is in a given domain, you have trust between environments with a third-party domain. But things get more complex than this. When in reality you take the business requirements and you start to decompose the key steps and identify the business demand tells you that the device has limited resources. Therefore, in a PKI sense, to assume that you can support a 4-layer PKI with all of the certificates with insufficient memory to store it, to assume that you can actually communicate on a regular basis and patch the keys when it runs in a battery, it only comes online a certain period of time, immediately means that the PKI architect or the system architect is not meeting the business requirements. An impact analysis must be conducted within the given business case to identify the lifecycle aspects of a PKI to understand if a certificate, if compromised, must be revoked. For example, the ability to remove trust in a certificate in some environments is essential, and in other environments, the complexity of adding that capability outweighs its benefits. So there's a clear link between the business line and the architect trying to work out the design from an architectural perspective before you look at the technology. In the PKI world, it is likely that multiple certificates, multiple PKIs will be used. It is likely to have a PKI that acts on external interfaces, acts within a domain of the IT environment, and also potentially within a closed user group via a gateway within a specific environment. This supports a number of options for every IoT business owner. The local PKI that is used for the IoT environment can be part of a closed user group for which they have full policy control, yet external certificates that have to comply to other requirements or have to have other trust relationships can be purchased from other PKIs. Seeing each part individually does not allow you to see the whole. By not looking at the whole environment, you're in danger of missing some of the interrelationships. Each PKI, though, does have a life cycle. Each component in the PKI frequently has its own life cycle. These life cycles are essential. They're effectively ticking time bombs, waiting to go off. The expiry of a certificate is pretty much what you would expect. A certificate expires. PKI theory says you're not allowed to trust a certificate if it expires. In practice, you have to ask yourself, what if I did? Am I allowed to take the trust that was inherent in the certificate and assume that it still has a level of trust and continue to use it? This is a policy decision that requires the business to make an active choice. But when you look at the expiry of a certificate, this in itself is not enough. You have to look at the expiry of all of the other certificates that you're reliant on. That includes the issuing layer, the root layer, and others. You have to look at the life cycle aspects of you authorize the use of a certificate, but how do you deauthorize the use of a certificate? To deauthorize the use of a certificate, by classic PKI theory, you issue a revocation, it goes in a CRL, and it may or may not go into an OCSP responder. All of these changes change trust relationships. They change security strategies. They change security services. But each and every single one of them can break your operational model, or break your business model. It's been many years, the examples quoted here, when the big guys have learned that it's easy to miss one. Google, Microsoft, HP, Apple, they've all ended up with operational impacts where they've had to, in crisis mode, go and fix a particular certificate. Either accidentally added it to a CRL or lost control of a key. In an IoT environment with 500 million devices out there, how would you react? You cannot go to the terminal to make a fix. PKI in an IoT environment is typically fully automated. The IT industry has learning more and more that they must automate certificates. They must automate the key management. In the past, an external website could easily be managed manually because you only had a few, and you manually got the certificate, typically from a public PKI, following manual processes. Heavy on the process, light on the technology. As PKIs have been introduced more and more and more to the back-end infrastructure, and in particular in cloud, and are now used on platforms such as Kubernetes with short-lived certificates for microservices, the automation becomes essential. In an IoT environment for the scalability, automation will also have to be essential. There are two main protocols currently being used for automation. SCEP, which is used for routers, switches, and other hardware devices, and ACME, which is used for Let's Encrypt predominantly at the moment for outside websites and others to auto-renew their certificate. But the authorization process to give the right to get a certificate is still reliant on a secret of some kind. In the case of SCEP, it's typically a password. In the case of ACME, it typically is a link to the DNS. But in the case of an IoT environment with hundreds of millions of devices from multiple PKIs, managing secrets is extremely difficult. Having a DNS structure that works along the same approach, they're not websites. That also is very difficult. The CA will automate the generation of keys, and that is particularly important when manufacturing. The key generation, the most efficient is to do it off the device and inject it. The RA may generate the keys, the RA being the registration authority, for distribution and forward of the request. This can be done asymmetrically before manufacture. A local RA-CA can do both together within a factory, but may change the architecture at large. Because if you have 5 factories, that's 5 CAs with different trust relationships, and this may or may not add a layer of complexity to the CA architecture. In case you have multiple CAs that ultimately issue the same certificate, or it looks the same, they're by policy the same, but technically they may or may not be different. In particular, serial numbers would be different. These are uniquely linked to the CA, or they're issuing from a CA that you do not control. There is the use of a policy OID. A policy OID is a unique identifier that links a certificate to the policy under which it's issued. This is very, very valuable when it comes to validating in a low resource environment. Rather than checking the FQDN, all of the attributes, and comparing against a whitelist to create a group-based access control, a policy OID can indicate that that policy links to a group of registered devices and then gives you the ability to treat it as a group, even if this is issued from a different PKI. This allows a future-proof capability built in. So policy OIDs should be considered when planning this. That, however, does bring the need to have good policy management and good governance, which is not a technical issue, but it's a governance, risk and compliance type of issue. I'll give you one example, code signing. The business demand for code signing is to have code that is A, trusted, it's authorized, and is ideally immutable. That is, it cannot be modified from its distribution point until it's in the IoT device. The capability to do so requires a series of processes to actually generate the code, sign the code, and deploy the code. This is a typical functional view you would expect from any architect or IT developing code signing. It does not, however, show what happens when you revoke a certificate. Recently, Apple revoked a certificate and blocked all the drivers in the HP so that you can no longer access the HP printers. These are two organizations that wouldn't call each other just because of a technical certificate revocation, but had a significant impact on clients, on customers. How would IoT service providers manage this when another service provider with a different interest was to revoke a key? The impact may or may not be easy to see, but the lifecycle change is easy to understand, and the questions can be asked in preparation. The idealistic view of all architecture is, by definition, idealistic. You look for elegance, and everyone thinks the elegance is there, and all architects aim and aspire for this. IoT is no different. However, the reality is, along the fable of boiling the frog, you slowly change things that you don't notice till eventually the frog dies. If, however, you threw it in the hot water, it would jump straight out. Most architects recognize, most banks and infrastructure recognize, the tactical evolution of how they created their environment is not the idealistic sense that's there. Architects learn from the physical world. That means building houses. They've been around for many, many decades. Yet a house, the mystery house, over a 38-year period, had hundreds of builders, 0 architects, and now nobody knows the reliance, no drawings, what is relying on what. There are lots of IT systems out there like that. The difference is they're not sitting with self-exploding bombs in them. Certificates buried under the infrastructure covers means that you can't see them. That couldn't happen in IT? Not true. IT starts with an elegant ambition, the wonderful wiring. The reality is it ends up through time, add a wire, add another one, until you can't see it. The strange bit is the colour coding of a complex wiring loom, the one that's there that looks out of control, may actually be easier to diagnose sometimes than the one that's all using the same colour, because you can't tell the difference between them. So colour coding certificates, as shown in the diagrams previously, for an architect actually can provide value. Printers on the Mac, easy. Try it on a fridge, a thermostat, worst case a heart monitor. How do you stop these IoT devices to allow you to patch them? There is no single design authority, no aligned policies, no aligned capabilities. It's very, very difficult to see what's connected to what. The nirvana of all IoT devices connected to each other will require very significant oversight from a cryptographic perspective and a PKI perspective. One example is the trust store. Who are you going to trust? The trust store is the fundamental trust of every PKI. When you put the self-signed certificate into the trust store, you inherit the trust that goes with that, which if it's abused means they can both listen in, adjust and modify and issue new certificates. But the world is changing. Google has decided to bring in their own CA root program. That means that the underlying operating system will no longer be used by them for a trust store. That means that in an IoT world, if you have a web interface by your user, you have to have your root in the trust store of Google. How would you do this? Well, nobody knows yet. One thing's for sure, Google is likely to charge for the service. So the future of how we do it, if you have a CUG, a closed user group PKI, you have to manage the trust anchor. You have to find ways to get it into the right places. If you use a public PKI, it comes with a variety of limitations that you can't control, that you may or may not want to customize for your given environment. The risk is that you have a client, a user, who has to configure a device using a web interface and getting errors. Recommendations are, don't focus on the P and the K, focus on the I. Cryptographic strength is where all the debate takes place. How big should my keys be? Should I use RSA or elliptic curve, especially on a resource-limited device? Yes, it's important, but in the operational sense, if a system is dead, it's dead. If it doesn't work, it doesn't matter the cryptographic strength, because people will just bypass it. So it's important on the cryptography, but lead from the business, lead from the product lifecycle, lead from the risk, lead from the impact. Understand and plan for everything that can go wrong. Do a what-if model. What if a certificate expires? What if I have to change it? What if? And get the life cycle right. Rigorously follow standards if they exist, but remember, most PKI standards came from a different era, a different world, and don't work the same way you'd expect. Train your architects. There's a difference knowing the path and walking the path. A lot of people out there believe they understand PKI, but when it comes to industrialized deployment, operation and management, it's harder and it's not so easy to do.